Okay, I think I'll start with the introduction. So welcome to this webinar, part of the webinars that we organize in the EATS Language Technology Center of the Basque Country, and by the chair, the University Company Chair of AI and Language Technologies. So here you can see the list of previous speakers. Unluckily, the last webinar was cancelled by Ekaterina. Well, not cancelled. We are trying to relocate another date for her. Today we have Sebastian, and you can see the list of next webinars that we'll have every month. So today I'm really happy and excited to have Sebastian here. I've known him from many years ago. Actually, I'm co-author of a paper with him where we were doing actually things which are linked to the topic of his talk, because we were working it was a position paper on how at the time cross-lingual word embeddings should be evaluated, and especially the unsupervised one, and the problems that arise when you are evaluating, and that's somehow related to today, because language models are notoriously difficult to evaluate, especially across languages. So Sebastian is currently a research scientist at Meta, I think quite recently at Berlin, and he's working on evaluation and benchmarking of language models. He led the multilinguality team at Cohere, where he was trying to improve the capabilities of Cohere language models, which I guess it was an important responsibility, because the models released by Cohere are notoriously strong. So that's a very relevant language models. And before that, he was on Google DeepMind, where he went after his PhD in NLP in Dublin. So, well, that's all for my part. Sebastian, it's now your turn. I'll leave.
Yeah, thanks so much for the kind introduction, Nico. Let me share my screen here. Yeah, can you see my screen? Is that all? Yep. Cool. I'm not sure I'll be able to see the comments during the talk, so please just yeah, if you have any comments, we can, yeah, if it's something urgent, we can take it during the talk. Otherwise, happy to take questions at the end.
Yeah, I'll check the chat just in case, but usually we will wait for questions to the end.
Okay, yeah.
And if there's anything urgent, yeah, I can take them.
Cool. Yeah, all right. Yeah, so today I want to talk with you a bit about how we evaluate multilingual large language models in real-world applications. And so this is quite relevant at the moment in the current work of Meta and working in this direction. Sorry, I'm getting a bit of echo here. Okay, I think it's fine. Right. And so this talk is mainly going to be about my prior work at Cohere, but also it's relevant to what I'm currently doing at Meta, and I'm happy to talk about kind of different challenges at the end as well. So just regarding what I did at Cohere previously, I worked on developing and improving the multilingual capabilities of Cohere's models. And Cohere, if you may know it, it's a startup that works on large language models, and particularly with developing these models for business applications. And the multilingual models that we developed also mainly focused on languages that were widely used in businesses, with 10 priority languages here that are spoken around the world. Some of the models that we had released last year, you might have maybe seen or even used in your own work, like Command R and Command R+, which was, upon its release, one of the top models on Chatbot Arena, as well as some updated models and smaller models. And Cohere also has this separate dedicated research lab called Cohere for AI, which is also focused on a lot of multilingual research. And in particular, it has also released these multilingual models called Aya and Aya 23, which really focus on improving these multilingual capabilities. And just to give you a bit more context on the work that we were doing in the team, basically, in terms of improving or working on multilinguality, I think this really spans not only at Cohere, but also in other places. spans every component in the language modeling stack, from pre-training to post-training, and then deploying those models and adapting them for specific customer applications. And two areas that are relevant kind of in all these components is both getting the data, right? So you want to have high quality multilingual data here, and you want to be able to evaluate your models at every point in the stack. And so for this talk, I'm mainly going to talk about evaluation here, and specifically certain considerations when evaluating these models for multilingual performance. Now, just to give a bit more context on the general landscape of multilingual language models these days, you're probably familiar with kind of a lot of the standard benchmarks, like MLU here, which is a benchmark consisting of exams across a lot of different categories. It's multiple choice question answering, and it's used as a general measure of how the knowledge a model contains. And you can see here kind of some scores from benchmark state-of-the-art models. On the multilingual side, a lot of these benchmarks that have been that these state-of-the-art models have reported results on are typically analogs to these popular English-based benchmarks. So for instance, there's a multilingual MLU version, which is just a automatic or human translation of the English MLU. And we can see here that for evaluating these models, there's generally still a gap in terms of how well these models do in English versus how they do on this translated or multilingual counterpart. And we can see this gap on different other data sets as well. However, if we look to larger models, so if we go from 70 to the 405B for Llama, or from Sonnet to Opus, we see that this gap slightly decreases. So as models get larger with increasing scale, also the benchmarks slowly saturate, but also the multilingual capabilities increase. And we see similar trends for other benchmarks in the multilingual counterparts, such as the mathematical reasoning dataset GSM-8K and its multilingual version, where we also see still a gap towards English, but this gap again kind of reducing as the models scale up. However, with that in mind, I think what we have to be aware of is that these existing benchmarks that are being reported on the state-of-the-art models don't really capture a lot of the complexity and nuance of actual natural language across different languages of the world. So a lot of things, just by virtue of being only translations and only capturing the English, mostly English-centric knowledge that is captured by the original benchmarks. So in the future, and we already have some promising threads in a lot of these areas in order to really make sure that our models perform reliably and naturally in a lot of languages. We need benchmarks that kind of respect the constraints and needs of users in their own languages, that also capture cultural and common sense knowledge, as well as the values and norms from people across the world, and that are also representative of, for instance, different topical preferences or what is considered taboo or misogynistic in different languages, as well as different definitions of hate speech, for instance. Yeah, basically just as a reminder here that while these models have improved a lot multilingually, there's still a lot that is not currently captured with existing evaluations. So with that in mind, I want to talk about two aspects in this multilingual evaluation space. On the one hand, looking at a kind of more fundamental evaluation in a conversational focus, and on the other hand, looking at how well efficient models or quantized models perform across different languages. And both of these works also have been presented at ENLP last year. So starting with the first focus here, if we think about having a general purpose dialogue agent and language model that we can interact with in any language, and we can kind of think of a couple of constraints or requirements that this model or the output of this model should have. In particular, the model should understand the intent of the user, and its response should be generally truthful. So in terms of its content, it should fulfill certain considerations like being truthful, being coherent, not overly verbose, right? Concise, have all the required information in there. And also the form of its response should be appropriate, right? So it should not make any grammatical errors. It should not respond in an overly lyrical style, maybe if that's not desired. The tone and register should be fine as well. So all of these constraints we would like our response to fulfill. And in practice, there's been a lot of attention on the first part here. So evaluating, for instance, how truthful a response is, whether the model hallucinates, which has been a very active area of research and is traditionally quite difficult to evaluate. However, there's been less focus on the second type of errors, so errors more on the form side, because in English, models tend to make less grammatical errors, for instance, which doesn't mean that these errors may not occur in other languages. And still, even if a model only makes errors in the form, these still can lead to a breakdown in trust if they're severe enough. So for this study, we basically, in our interactions and kind of developing these models at Cohere, we identified one limitation in form that is very fundamental and very basic, but that we still found to reduce a lot the utility of these language models when we're actually interacting with them in different languages. And that characteristic is basically being unable to generate in the language that the user required or that the user was asking for. And we termed this language confusion. You might also, or this might also kind of evoke the concept of code switching, right? So code switching, as we know in human conversations, is if people switch between different languages, either across utterances or even within the same utterance, which is a natural phenomenon and something that's common in multilingual societies and something that we also want our model to exhibit. And in contrast, this language confusion here is a kind of artificial version of code switching. So it's a kind of error type that the model makes and that we explicitly do not want the model to exhibit. So to give some examples here, we've seen this basically, and this is probably the most difficult type to identify in practice, is if it occurs on the word level. So this is a Korean query, just asking the model to generate a response. And the model generates a semantically meaningful response here, but then arbitrarily in the middle switches to an English word and then switches again back into Korean. And the English word is meaningful in context. So if you would translate the response to English, this would in the middle would make sense. But of course, it's completely out of place here in this response. We've also seen this behavior not just with our own models, but also with other state-of-the-art models like Llama 3.1 here, where here, for instance, the model responds to a Russian query, and again, kind of seemingly randomly switches to English for a few words, and then continues again in Russian as if nothing happened. And this behavior we've seen can occur in different levels. It's kind of most obvious on the full level of the entire response, where the model might typically just ignore the source, the query language entirely and just respond in English. It can occur on the level of lines, where the modelers might switch the level of a line or a sentence into different languages, or it might occur on this level of individual words. Because we weren't able to find any source that was already like targeting or evaluating this behavior, we basically curated our own benchmark consisting of a diverse collection of both existing prompts with different nature. So we both kind of curated prompts that were human generated as well as translated and post-edited, and also created our own prompts based on some of our internal annotation studies that were more complex in nature, because in some of our early experiments, we saw that this kind of behavior in terms of switching the language or getting the language wrong often occurred if the model was struggling or dealing with more complex prompts in practice. And the benchmark and the prompts are publicly available, and they cover basically 15 different languages. And the two settings that we're evaluating here, monolingual and crosslingual, are basically kind of the monolingual setting is what I already showed in the beginning, where we have a user asking a model a question in their own language here, and then expecting naturally a response in the same language. The other setting that we also wanted to evaluate was this cross-lingual generation setting, where we create a question in one language, but we ask the model explicitly to generate a question in a different language. And in practice, we've seen that particularly if you have one application and you want with a certain prompt, and you want to serve users in many different languages, it can be really useful here to basically have just a single prompt template, typically in English, and then just use the language as a parameter that you can then fill in at runtime. So you also, so having these models be able to follow this cross-lingual instruction can be really helpful for these sort of very multilingual applications in practice. For evaluation, we initially just wanted to, or in our initial experiments, we were just using accuracy, basically, just looking at the fraction of lines that were predicted or were in the correct language, or the fraction of words that were in the correct language. But because often this behavior is quite, it can be quite rare, and depending on the model response, right, if the model responds with multiple paragraphs and only like a single word or single sentence is in the wrong language, that might maybe belie the actual severity of this problem. And so, because even in a very long response, if there's only a single word that is in the wrong language, already that can make for quite a bad user experience. We're using a binary metric instead here, which basically counts a response as an error if there's any occurrence of either line level or word level language confusion, right? So in practice, we basically just have this binary metric here where we identify all the lines that are correctly identified, or we identify the language of all the lines in the document, and we only give credit for responses where all the lines are in the correct language here. And for the line level, we basically just use what we found in early experiments was the most robust method for line level language identification, which is the open source fast text here. Now for the word level identification, as you already saw before, and kind of based on prior studies in the literature, is kind of a more challenging problem to reliably identify the language of each word in a sentence. And so to make this tractable, because current even state-of-the-art models only reach about 90 or 85% accuracy on this task, we basically try to narrow down the settings where we want to detect word level errors. And because in practice, we mostly or only observed word level errors in languages that have a different script and them switching to English. For those languages, we basically just use a filtered English word list. Yeah, so and just check whether any of those words that are in this curated word list that we created are in the model prediction. And for languages that are in the Latin script, we basically we can't reliably check if there's an English word there because of so many loan words that are being used across these languages. So in those cases, we just look for switches to different scripts, just using the Unicode code points here. So in practice, this doesn't cover all the possible errors, but we found that these were still reliable and useful enough for our evaluations, and still useful enough to actually highlight issues in state-of-the-art models. So for results, we basically performed experiments with 4 different model families: Llama models, models from Mistral at the time, Command R models, and some models from OpenAI. And we can see here, these are for monolingual generation for line level pass rate with nucleus to top P sampling with some default temperature choices, which we also ablated later on. And here we can basically see on the monolingual line level setting that even kind of the best models still no model reaches completely 100% here. So even the best model still exhibits some degree of language confusion in this kind of very natural setting where a model just needs to respond in the same language as the input. And we see that some models are actually surprisingly bad at this behavior, even in this very simple or very natural monolingual setting, in particular the early Llama models and all of the Mistral models. On the cross-lingual setting, because this is less kind of less naturally learned in pre-training, but more closer to an instruction following behavior. We can see that all models do worse at this. And we can also see that the models that actually suffer the biggest degradation here are, compared to the monolingual setting, Command R and Llama 3.1. For Command R, we can say that the reason this performs a bit poorly here is because we are only able to reliably evaluate or identify these errors after we had already released this model. So by updating and kind of incorporating some of the findings, we were able to improve Command R Plus a lot on this behavior. But for the earlier Command R version was a lot poorer still on this evaluation. So just kind of looking a bit more at some of the particular like per language trends here for Llama 3.1, for instance, in the cross-lingual setting. We can basically see here kind of two categories of languages that perform. So the green languages are languages the model has seen during post-training, according to their tech report, and the red languages are languages that the model has not seen during post-training. And so we can see here that generally, if a model has been post-trained on these languages, it tends to perform better. And among the unseen languages, the languages where it still performs quite well on are Indonesian and Vietnamese, both using also Latin script. So it seems there's some sort of transfer on the script level here, and all the other languages in which the model performs poorly are languages which use a different script. So for the model transferring badly cross-lingually to those languages. Now going from the line level to the word level behavior, we can again see that all models do actually relatively well at the word level confusion here, particularly on the monolingual setting. The only real exception kind of across the board is the mixture of experts model, which performs relatively poorly. And just to say here, so to make these word level results kind of informative, we actually disentangled them from the line level results. So everything that is already line level error doesn't count as a word level error. So word level errors are really only errors where individual words are switched in the entire response. And so here, we don't know exactly why this mixture model performs that poorly. I think one potential explanation could be that it's the only mixture of expert model that we evaluated. So perhaps some of the like token level routing in this mixture of expert model might make it more susceptible to this sort of language confusion behavior on the word level. We can also further look at the impact of the different sources that we curated the prompts from. And specifically, we can kind of see here, if we look at the average performance in cross-lingual generation, that by far the most challenging prompts in this cross-lingual setting are the more complex prompts that we specifically annotated for this data set. And on these, kind of all models across the board perform relatively worse. We can also compare the performance of base and instruction-tuned versions of model families where both versions of the model are available. And the interesting point here is that post-training significantly affects this behavior, but this can be different across different language families. So for the Llama-based models, we can see that actually the base versions have very little language confusion. And that the post-trained models are much worse now at this behavior in the monolingual setting. So for Combined R models, we can see the actual other opposite, that the base models are relatively poor, but the post-trained versions do much better on that. And I think the main factor that seems to explain this here is that because for the Llama models, the post-training was essentially only English-centric or used mostly English-based data. So the main errors that the Llama 2 and Llama 3 models here make are actually, regardless of the query language, just responding in English to any language, any query that you give it. And in contrast, the multilingual post-training that we applied for Command R and Command R Plus improves this behavior a lot. So just finally, we can also develop a bit more intuition when these type of word level switches actually occur in a predicted sequence. And to that end, we can plot a couple of statistics, in particular the entropy, so the uncertainty over the token predictions. The number of tokens in the nucleus that are seen here in brackets here are at different sampling points. So the nucleus here is basically just the top n, the words that have together when the probabilities are summed, the kind of top p of the probability mass. And kind of intuitively, right, the model makes an error on the word level here if a token in an undecided language has sufficient probability mass that it's included in this nucleus and then kind of randomly sampled from there. So basically, as you might expect intuitively, the chance for these word level language confusion errors are the highest when the entropy, so the uncertainty of the model of what to predict, even in its own language, are relatively high. And there are comparatively many words in the sampling nucleus, which increases the chance of sampling one word that may be in a different language. However, and maybe one behavior that we didn't really analyze here is what actually leads to this type of behavior, or these like English words, for instance, receiving that high probability relative to all the other words that are in the same language and should actually be more appropriate here. And these might relate to under calibration, or simply the probabilities of words in different languages not being properly calibrated, both in the same language and also with regard to English, which can lead to this behavior potentially. Finally, there's also some things that we can do at inference time to mitigate this behavior. We can both adjust the temperature. Yeah, so if we reduce the temperature, basically by reducing the size of the nucleus and sharpening the overall probability mass, we're gonna sample only like a few words and make it less likely that some low probability English words, for instance, are sampled by accident. We also saw that reducing the nucleus size can have a small effect. And finally, actually doing kind of more expensive decoding strategies like beam search that kind of maintain different beams and actually look at the probability mass across the whole sequence also reduce this behavior, however, at a higher computation cost. And finally, there's also things we can do at post-training to improve this. For instance, doing fusion prompting is very helpful in just being able to mitigate this behavior, both monolingually and cross-lingually. We again see kind of in our own ablations that if we just do English-centric post-training, we actually make this behavior a lot worse. However, if we do both multilingual SFT and multilingual preference tuning, we can again reduce this language confusion behavior. So finally, just want to end with a few takeaways from this section. Even though I think this basic behavior of just responding in the wrong language, I think is fairly trivial, I hope I'm still able to communicate that there's kind of more subtle aspects, particularly even as we look at word level occurrences, and that this behavior is present even in state-of-the-art language models these days. In practice, we can basically think of this as an underside side effect of sampling, and probably a result of kind of the standard, more English-centric post-training, and probably also more English-centric pre-training, which may lead to these different token level probabilities being slightly under or miscalibrated with regard to each other. And finally, I think one nice thing about this evaluation compared to the overall complexity of evaluating multilingual language models or just language model generations in practice is that it's very efficient and quite precise to evaluate in practice, at least for these quite well-defined scenarios that we were looking at in the study. And so I think it can really serve as a useful unit test and kind of baseline level of evaluation for making sure that our models are actually doing what they're supposed to do at inference time. And however, this kind of also opens this broader area of steering model behavior multilingually and making sure that models generate responses that are right, not only in content, but also in form. And this broad area is much more complex and also much more subjective. For instance, if it comes to evaluating whether a model responds in the right tone or in the right, like with the right perspective or like opinion. And so there's much more work to do in this area, actually, to make this both efficient and also reliable to evaluate in practice. So with that, can come to the second part of the talk now, which is also on multilingual evaluation, but now for a different category of models, in particular for models that are very efficient in practice. And we want to have efficient models because ultimately we really want these models to be available to anyone in any country across the globe. And for that, models must be able to function under the different constraints. So they must be quite lightweight and also highly efficient. And in practice, quantization is typically the most popular way to achieve this efficiency by compressing the model, and in order to improve its memory and also its throughput at inference time. But so far, it basically hasn't been clear how this quantization procedure actually affects the performance of these multilingual, like large multilingual models that are being quantized in practice. There have been some prior studies, particularly when new quantization methods are being proposed on English. But these also typically just looked at standard benchmarks that I mentioned before, like MLU, and not really any more complex generation tasks. Actually looking at how predictions or long form response generation, for instance, is affected. And so for this study, we basically looking both at multilingual evaluation, but also human evaluation to really get a more accurate and more real-world sense of how performance deteriorates or is affected as we do this, as we do different quantization processes. So what is quantization actually? In practice, it's basically just a way to compress the weights and also the activations of a model to representations that have a lower precision. There's two kind of paradigms. We can both apply quantization during training, so already train with low precision during the entire pre-training, post-training, or we can just train with full or like half precision, and then only quantize our models post-hoc after they've already been trained. The second part is kind of the most simple in nature because we already have a trained model and we just need to do this process. We can do this process mostly offline or on the fly, and which is why we're also doing it this way here. And so for the post-training quantization, there's also two ways that we can go about doing that. We can only choose to quantize the weights of the model and just quantize them offline, basically, and then just store the compressed representations that are loaded when we're using the model at runtime. This in practice leads to a smaller memory footprint and also allows us to do faster inference if we're limited by memory. And so in practice, what is basically just being done here is that we have a scaling factor that is just based on how many bits we want to compress the model to. And in practice, this just basically be scaled for each weight matrix based on the kind of largest magnitude of the matrix. So we now take kind of this entire like range of the values and basically just compress it to fit within these like 128 bits, typically kind of on both sides. So just in this smaller range, and hope that we don't lose out too much information in this compression process. From the weights, we can also additionally try to quantize the activations. However, because the activations are more unstable. This is typically done at runtime, so dynamically on the fly for each input, and allows us to use kind of specialized matrix multiplications on modern GPUs. And so for activations, this is basically kind of the same similar setting as before. So we again have for weights these different scaling factors that we can apply, and similar again per activation scaling factors that we can learn here, again, kind of based on the largest magnitude of our activation values. However, for typically, we often might lose too much information if we just use a single scaling factor for each weight matrix or for each activation matrix. So instead, for weights, we typically do this kind of on a per column level, and on and for the activations, for the inputs, we do this on a per token level, basically, to have some additional granularity and some additional flexibility in doing this compression. However, still, if we even if we learn or use these additional scaling factors, there's still kind of additional issues, particularly with the nature or the range of values and activations. So here, in practice, if we look at the distributions of weights in our models, these are typically in relatively small range and kind of quite regularly distributed here, while activations can be much more arbitrary and can have much higher range, with having some outliers as well that are much higher valued than the remaining values in the activations. And trying to compress these then just based on the prime methods before can cause us losing a lot of information by virtue of these outlier features. As a kind of mitigation measure, it has basically been proposed that instead of compressing these activations that much, instead we learn some additional scaling factor S here, where we basically kind of slightly increase the range of the weights and slightly smooth out further the activations here to then make the weights slightly harder to compress, but still relatively easy, and making the activations a lot easier to compress as a result. For the settings that we studied, we basically focused on the models that we had readily available, including Command R and IA models. And we looked at different kind of variants of the quantization methods that I mentioned before, including both different levels of precision for weight only and weight and activation quantization, as well as looking at some recently proposed methods like smooth quant and some additional more finely granular compression like per group scaling, where instead of having per column scaling factors, we have additional factors for even specific groups that are being learned in this method. And baseline, basically just the standard half precision weights. The benchmarks that we have evaluated on include both automatic benchmarks, such as MU and MGSM that I mentioned before, Flores for translation, and the language confusion benchmark that we introduced earlier. On the human and kind of more generative side, we are looking at an internal evaluation suite where we usually have 150 prompts that were translated from English that are quite challenging, and we have humans evaluate these. And we also have 150 prompts from the IA Dolly dataset that are basically instruction following evaluation that is multilingual that we also evaluate here. In both cases, so in the left case using human evaluation, in the right case doing LLM as a judge evaluation. One big takeaway from this study here is if we only look at automatic metrics here across different languages, we don't really see a strong impact of these different quantization methods measures or of the weight only 4-bit quantization, for instance. So in most cases, there's only slight reductions in performance compared to the full floating point P16. However, if we look at our human evaluation and kind of arguably more complex evaluation measures, we can see that there's a lot higher deterioration that we observe here, as if we ask humans to judge these, in particular for Japanese and French, but even for English, we observe much higher deterioration when I actually asking humans to evaluate these models. We can also see that there's a performance difference across the different languages, and here particularly classifying languages by Latin script or Indo-European versus non-Latin script languages. And we can see here that as the quantization becomes stronger or more severe, that the performance impact on the model or by language increases as well. So in practice, basically non-Latin script languages or languages that are underrepresented in pre-training are affected disproportionately during this quantization process. Also across tasks, where we have tasks sorted here roughly in order of complexity, We can also see that there's an impact that increases as tasks get more complex, or the type of knowledge required or the type of reasoning gets more challenging, with, again, the biggest degradation observed here for the more like long form generation or human or automatic evaluation settings. And finally, we can also see kind of the performance difference of the kind of standard method and the additional method with the mitigation strategy. And we can see, even though the differences are relatively small here, that on average, we still get kind of across the board some improvement from applying this additional smoothing to the quantization process. And similarly, having these more finely granular scaling factors with pro-group scaling also improves performance for the weight-only 4-bit quantization. So finally, I just want to highlight again here that it's really important for kind of global or wide adoption, particularly of open source models, to provide models that are efficient and high performance. However, and I think going forward, at least the current set of automatic measures really underestimate the actual negative impact of this quantization process. And even these widely used measures like weight-only 8-bit quantization still leads to the degradation that is detectable by humans. And if we quantize with 4-bit, that's even worse. So hopefully, kind of going forward in future studies on quantization, both multilinguality as well as kind of other more complex or outlier dimensions or domains are being considered, and not just performance on very standard benchmarks for evaluating and creating new efficient methods. And so finally, just a couple of final thoughts here. I think in general, I feel that we both need more complex evaluations, but at the same time, particularly as model capabilities continue to scale and grow more powerful, we also need to make sure that our models don't lose out on, and that we don't lose sight of even more fundamental blind spots and just kind of basic fundamental like table stakes capabilities, like being able to generate in the right language, or just having like not making any grammatical errors really, or basic like mathematical understanding in all like across different domains basically. We've seen, particularly in the last study, that automatic evaluations are sometimes not sufficient. But of course, really in the multilingual setting, it's kind of most prominent that we can't really easily scale to many languages by only relying on human evaluation. So I think, yeah, we should really take this more as a means to improve the reliability of our automatic evaluations and make them kind of more useful and more reflective of the actual trends we want to capture, and kind of make sure that they have high correlation to what we want to analyze. And finally, with regard to the kind of broader multilingual evaluation space, I think it's important to go beyond translation ultimately, right? I mean, while for sure there's going to be more progress on English-based benchmarks, and while translating these can be kind of a good stopgap measure or kind of a good baseline measure to get some understanding of multilingual performance, ultimately, in order to really make sure that our models are most useful in different languages, we really need to evaluate them on benchmarks that are language specific and capture those different language properties. So with that, thanks a lot for listening to my talk, and happy to stick around for some questions or have some discussion as well.
Okay, thank you, Sebastian, for this excellent talk. So we now have time for questions and discussion. Anyone who wanted to make a question, you can raise your hand. Okay, I have some questions of my own, but I'll start with the people in the audience. So Eleftherios, you can take the mic if you want.
Hello, thank you very much for your interesting presentation. Really good work. I have a first technical question. So in one of your metrics for the language confusion, the line level pass rate, for me, it's one of the first time I see to use the line as a segment for evaluation, granularity for evaluation. We used to have sentence level, word level. It's the first time to see the line. So how does this line get defined? Oh, it's here. Okay.
Hmm? Yeah, in practice, I think the line setting was basically, I think, more a setting of like convenience or simplicity, because in practice we know that sentence splitting is still not solved in many languages. So basically the line is basically just based on like new lines here. So in practice this can be like across multiple sentences, and this is kind of based on also because we observed that at least the off-the-shelf like language ID systems that we were using worked well mostly from lines that were like from 5 words or longer. So we have like a minimum like line length where we apply this metric to have high precision basically. And so yeah, because of that, to have something that is kind of between the level of the full document, like a bit more granular, but not needing the complexity of actually doing kind of reliable sentence splitting.
Okay, thank you. And I have a more generic question. So you present a very specific example of focused evaluation in a particular problem, and you also mention some mitigation methods. I have a more generic question. Like, do you think like the developers, also from your experience, the developers of LLMs really look at the specific evaluations, and do they have mitigation measures for each one of the problems that are revealed?
I can't really speak for like generally LLM developers, but at least from what I've seen in terms of developing these like foundation models or like larger models, I think so far there's definitely been more the trend of like you have measures, evolution benchmarks that capture very like high level behavior, like MLU, right? You know the general knowledge, but less insight into actually the different types of like errors or like failure modes of the model. And I do think in terms of like making models, like improving models reliably in the future, having this more fine-grained insight can inform like how we want to structure like post-trained data or what kind of data we need. I've seen kind of more demand for basically having like fine-grained measures so that can give you like fine granular insights, and even things like this where at some point with the models we have now, like at least in the monolingual setting, we have basically like mostly solved this, right? There's still these can still be useful to make sure we don't regress on it, right? If another team focuses adds a lot of English data, we want to make sure that we don't get worse at this behavior. But also, the current measure here, for instance, is just looking at this very basic setting, basically, and kind of as we in more realistic conversations, there's like multi-turn context, right, where people might switch languages. There might be like code switching on the language level. So I think there's also like a lot more complexity that we're not covering yet here.
Okay, thank you. We can have now questions from Ruslan. Can take the mic.
Yeah. Hello. Thanks for the presentation. It was very interesting. I have a question regarding the second topic you presented. And I have two questions. The first question is, did you observe patterns regarding types of text where the gradation was most noticeable when generated with quantized models as opposed to when generated with non-quantized models?
Yeah, great question. So for this paper, we didn't. Yeah, I think we looked. We looked a bit at the generations or at some of the human outputs of the generations, but there was not as far as I remember, we didn't really identify any more underlying patterns that were shared across more generations. In practice, these were kind of side-by-side evaluations. So people basically decided, I prefer this generation versus the other one. And I was also kind of hoping that there would be something in something more tangible maybe, but this was a bit difficult to get at least with this kind of broader human evaluation.
Okay, thank you. Mark, can take the mic?
Hi, yes, I am Luis. I'm using Mark's computer. So could you go back to the Llama 3 results for linguistic confusion, for language confusion. If you
These ones or the ones before?
Yeah, this one. Yes, the next one. And the long table. Yeah, the one where you mentioned the seen and unseen languages.
Okay, yeah.
Yes. So it says, you say it performs very well in Indonesian and Vietnamese. However, I was looking at the origins of the monolingual data, and both Indonesian and Vietnamese come from synthetic generation and machine translation. So would it be possible that it's actually not performing very well in Indonesian, but in like translation is Indonesian, and like that the transfer does not come from competence but from translation is?
Yeah, I mean, yeah, it could be possible as well. But I guess in this setting, I mean, we like I said here, we were looking, for instance, a bit at like here the difference of like translated. I mean, so Okapi is like translated. ShareGPT is these are I think in different languages. So I mean, we looked at like the impact of translation. We didn't really observe much of a difference between translated versus like human-generated benchmarks necessarily. And I mean, given that this is with this behavior or with in this evaluation, the models try to continue the evaluation rather than maybe understanding it directly. I'm not sure how strong the impact of translation is necessarily in the prompt, but yeah, it might be like a conflating factor.
Yeah, and another question, just more in general about the state of the field and the impact of translation is, so this last year, like synthetic data has risen a lot. Like people want to use a lot of synthetic data for pre-training and for post-training. However, do you think this is a good approach for the multilingual setting, given that a lot of this data is coming from models that even if you ask them to generate things in Spanish or Basque, they will introduce a lot of translationists? Do you think it's a good idea to use synthetic data coming from models that are good at English and almost nothing else?
Yeah. I mean, that's a good point. I mean, I think it's. I mean, I think it's comes again down to like I think it's similar to the general question of, okay, how do we want to use synthetic data? What are the implications, like biases in the synthetic data that we use? I think like multilingually, there's definitely like other, like it's more English-centric biases there. Although I guess you could maybe you could suppose that if you have a model that, based on your other metrics, is able to generate fluent or text that is like relative like rated relatively natural by speakers of that language, that might be like sufficient to generate like synthetic data for. But I mean, even I don't think we have a good like I think with these models, I feel there's it's very fuzzy, right? What is translationese? What is like synthetic? Because it's like unnatural, like what is not translationese, but like modelese, or unnatural because it's translated from a poor model. So yeah, I don't think we have a good understanding of the different, like this spectrum here. But yeah, I think I'm generally a bit like, I think it's a potentially it opens up a lot of room for potentially overcoming some of the data scarcity in some languages. But I do think that there are definitely concerns regarding the quality of the data, if not properly vetted.
Okay, thank you.
Thank you, Mark. I have a question of my own, a couple of questions actually. So in the language confusion mitigation experiments, you tried things at inference, I think. And I was wondering, because actually you mentioned later, and it's a well-known fact, but it's nice to see data, but that automatic evaluation and human evaluation sometimes don't agree. So I was wondering, at inference time, you were using, sorry, I think you mentioned temperature Yeah, okay, temperature and the nucleus size and beam search. So did you check whether this affected the quality of the responses generated for prompts? So did you use some human evaluation, or maybe you have some feelings whether these changes in the temperature and nucleus size affected the quality?
Yeah, we didn't. I mean, so we didn't specifically like validate this as part of this study here. But yeah, definitely. I mean, I think the most what we had seen like previously was definitely that the temperature affects the I guess creativity or like the a bit maybe surprisingness of the output, so that the output could potentially be more generic if you just do it with greedy or like temperature equals 0 decoding. But yeah, I don't remember the particular like results in terms of the difference here. But yeah, that has so here. I mean, yeah, this is just on this language confusion behavior that definitely needs to be taken into account how that affects like the output space or the general response quality.
Mm-hmm. Yeah, well, in fact, right now it's a pain to do this kind of experiments, because when you cannot trust the automatic results, then having to go to human evaluation, it's really complex. So,
Yep.
sorry, it's happening to us as well. And then I had another more general question. So it's very surprising. I found one of the most surprising things is that in the quantized versions, you had a very different drop depending on the language. And I don't know, I would have expected larger drops for, I don't know, smaller languages, but not for French. I was a bit surprised. But well, in any case, is not. Yeah, also English that in the middle. So I was surprised, and that really stresses that multilingual evaluation is something to be taken seriously, because if you only trust English evaluation, then you might have you might be missing the point of serving a multilingual language model. And in general, I know this is a very general question, but it's one which we have constantly here in the Basque Country. So that there is this idea that these foundational models should serve many languages, and you did a great effort to extend it to 100. But well, it's clear that you cannot extend it to the 7,000 languages in the world, right? But maybe one could expect that it could work generally well for 100. But is it really possible that the performance across all languages is similar? I don't know what it really means to be similar, right? But imagine a user using a language model in Basque or Spanish, and another one using it in English. Can we expect, maybe not now, but in the short future, that they will provide the same quality of answers in all languages?
I mean, yeah, I guess it comes down to what you,
general,
all languages, like 100 languages. I mean, I think there's definitely, yeah, I think we've seen, like from experiments that we've done in the past, there definitely needs to be some like certain threshold level of pre-train, like amount of pre-training data that you need to have per language, plus in general, I mean, there's some cross-lingual transfer and post-training, but still having some like post-training data in a language is also helpful to make sure like the model has down the instruction following behavior in that language. Yeah, and I think, I mean, of course, having that fraction kind of be like reasonable relative to the overall pre-trained data mix. I do think it's reasonable to kind of get to that level for like, I don't know, like 20, 50 languages. I think for 100, we're probably, I think that may still take a bit, but I think I think within that space, I do think this is possible. But also kind of acknowledging that there's more, that it depends on like the definition of what goodness means, because like right now we're not dealing really well with like dialects or other types of like certain kind of other notions of language beyond kind of the very general like monolithic like on the language level, and also in terms of maybe for like standard instruction following standard reasoning, but for more maybe fine-grained behavior, again, you want to really make sure that all of these are like exhibited well across languages. So I think even like on the evaluation side, there's I think you get a lot from transfer, but still, I don't think we have sufficient evaluations to really have like certainty that the model does not regress on any of its like huge number of capabilities in different languages.
Mm-hmm. Okay, thank you very much. It's about 4 now. I don't know. I guess you have to hurry to some other thing. There's a hand raised. So if you have a couple of more minutes, Sebastian, it's up to you. I don't want to.
Yeah, I need to go like in 3 minutes or so. But I can take like one more question.
Okay, so Luca, go ahead.
Hi, thank you for the great presentation. Just a very quick question, and don't worry if you need to go, if you can answer. My question was regarding how can you distinguish, if I lost this piece of information along the way, proper code switching from what I read in the paper confusion points in the cross-lingual setting. So if I understand correctly, you ask in English the model to answer in, for example, in French. What if in the answer, for example, in English title of a movie is mentioned? Is that counted as a confusion point?
Yeah, I mean, great point. So in practice, we kind of observed, okay, there's a lot of, particularly in in different languages, like English, English movie names or names of people, also like company names, all of these things also used in like Japanese, for instance, or simple like acronyms. So we, to make this basically more precise, and I think we have some more details on the paper, and hopefully, I think the word list that we use should also be available on GitHub. If it's not available, you can ping me, and we should also release that. So we basically had, for making this as precise as possible, started with this word list, and then basically removed any I think like proper nouns that we observe basically are kind of generally established in like in Japanese or so as being used in English. And so it's basically a lot of these are like kind of filler words or things that like individual words like here would, or just standard like nouns, verbs, like adjectives that would not be kind of part of like a more proper noun. Yeah. I don't think and I need to double check if there's anything specific for if there's like a movie name that we did. I mean, and I think the other point was we basically filtered out from these prompts questions that would in the response have the model mention like some English entity or like some English national park or like English movie names or so, right? So we try to filter these out so that the model would not respond with anything that would have like an English name, because I think in practice, if you would apply this to like a open-ended generation, I do think there's like a lot of these false positives that you might be able to capture, but basically by having this more constrained evaluation setting with really just settings where there should not be any English movie names or so mentioned, I think the metrics of the evaluation that we have is like relatively high precision in that regard.
Okay, interesting. Thank you so much.
Yeah, thank you, Sebastian, for your great talk and your interaction, and also for these few minutes. We know you're busy, so thank a lot for having here in the webinar. And for the rest of the audience, I will post now a slide with just for those who are interested with the list of next webinars in this course. Okay, thank you so much.
Yeah, thank you so much for having me, and excited to talk with you in the future also about vast language models. Sorry, we don't have more time today, but maybe we can do it at like ACL or another conference.
Okay, yeah, see you. Bye-bye.
Bye.